Assalamu alaikum wa rahmatullahi wa barakatuh. Can you hear me?
Yeah, we hear you well. Go ahead.
Very good. Thank you very much for the good introduction. And I would like to thank also Mr. Abdullah Shamrani for the very informative presentation, haqiqatan. Thank you all, and I think I'm gonna try to utilize my half an hour as most effectively as I can. So my presentation today is actually about the downtime element and the reliability equation. As we know, the reliability and the availability of equipment depends on how frequently they fail and also how fast you put them back in service, which means that the downtime element is very important. Sometimes when we look at reliability, we focus more on the mean time between failure, and sometimes we don't look, we don't look as much to the downtime element. So I would like to today to just shed some light on the downtime and its importance. I think enough about the presenter background. I've been introduced by my colleague here. So I would like to start with an illustrative case study. I'd like to bring a case study, and I'll try to illustrate the importance of downtime based on this case study that we actually handled about 15 years ago when I was with the consulting services department. As you can see here, there are 6 pumps, 3 big ones rated at 60,000 GPM and 3 small pumps rated at 35,000 GPM. And what these pumps do, they take water from the sea and they pump it into an inlet canal. And from this inlet canal, there are other high lift pumps that take the water, and it's used basically for the cooling for the whole facility. So if you lose the cooling of the facility, you lose the facility basically. So as I said, these pumps, 3 of them are rated at 35,000 GPM, 3 are rated at 60,000 GPM, and normally 2 or 3 pumps needed depending on the capacity of the available pumps basically. The normal mode of operation is what's needed is 1 big pump and 1 small pump. So that gives what? 60,000 plus 35,000, that's a total of 95,000 GPM. That's the normal mode of operation. The required capacity is 80,000 GPM, which means any excess amount is diverted back to the sea basically, to the outlet canal, and that is considered waste of energy. So these pumps, very old, over 50 years basically of age, and the time spent to repair them was taken a very long time due to major component failures and waiting for custom-made spare parts and so on. And so all of this basically raised concerns about their capability to sustain the required level of availability. So after looking at this problem, so what is it? First of all, we need to formalize this problem. So to understand it better, we need to put some sort of formalization and basically a means to measure the magnitude of the problem. So what is this problem? Is it a reliability problem? Is it an availability problem? Is it a maintainability problem? How are we going to formalize it? Basically, and is it an MTBF problem? Is it an MD town problem? All of these, unless we actually link them to some sort of business case, they mean nothing basically. So before we go, let's establish, me and the audience, just a little bit of common ground and understanding of the meaning of these different things basically. So what is reliability? And how is reliability different than availability? What is maintainability? and what are the parameters are actually needed to calculate either the reliability, the availability, the maintainability, and how do we link them basically to a business case, to make it a business case. So I'll start with the meaning of reliability. So what is reliability? Normally when I ask this question, I get so many different answers, but the reliability is the probability of achieving a certain mission under a specified condition. And what does this mean? Let's say I am in Bahrain now, okay? And I have a car. And what's the probability that my car will be able to make it to Dammam? Dammam is like what, 50, let's say 10 kilometer, 15 kilometer away from here. The probability of my car probably is a high probability. But when I say what is the probability that I will have a problem-free going to Riyadh, then the reliability will be lower. If I go and say, what's the probability to Jordan or to Cyprus, then that is going to be lower and lower. So as you can see, reliability is a function of mission. It's how much mission you want to actually achieve. So that's what the reliability is. Our example here is in kilometers, but normally for equipment, it's the mission is time. What's the probability that I will be able to run my equipment problem-free for the next year, or for the next 3 years, or for the next 5 years? So that is what reliability is. And there is an equation for it. If you want to assume an exponential function equation, then this is the equation for it. Reliability is equal E to the minus T over MTBF. So this is where MTBF comes along in the equation. So the question that we asked, what is the probability of achieving your mean time between failure? Let's say your mean time between failure is 5 years. So I put equipment now new. What's the probability that I will be able to make 5 years trouble-free? Many people, the most answers that I get in the classes and things like this, they say, well, maybe 90%, some 100%, and so on. But actually, if you plug it into this formula, your probability to achieve your mean time between failure is nothing really more than, well, according to this, if you plug one here, sorry, if you plug MTBF here divided by MTBF, this value will become -1. E to -1 is 36%. So the probability that you will be achieving your mean time between failure is only 36%. And that makes sense. When we say mean time between failures, that means the average time between a failure and another. And what's the average? The average is the average. So normally at 50%. So we only have 50%. In some cases, you exceeded the 5 years, if that's the 5 years is your average. And in some cases, you did not exceed. That's why you get an average of 5. So that's what a reliability is. So how is reliability different than availability? Availability is, in concept, is very simple. It's basically the uptime divided by the total time. So the uptime, in average, is the mean time between a failure to another. So the MTBF is your uptime, and your total time is basically your downtime here plus your uptime. So that's basically what availability is. Maintainability is similar concept. It's just the probability that a system or element can be repaired within a specified period of time. You set up a specified period of time. So what is the probability that you will be able to do that? And it's also a function of time. So if you combine all of these, summary, reliability is a function of MTBF normally. Availability is a function of mean time between failure and mean downtime. And maintainability is a function of the mean downtime, basically. So how do we, in our case study here, is it reliability? Is it availability? Is it maintainability? apparently it is actually an availability problem. So this is what we chose to model the problem. Now, when we want to calculate our MTBF and mean downtime, because if we want to calculate availability, reliability, or maintainability, we're going to need to be able to calculate our MTBF and mean downtime. So what is MTBF? MTBF is basically the total time divided by the number of failures. So if you have a period of in 10-year time, for example, we have 5 failures, so your mean time between failure is 2 years. And of course, you need to adjust for it if there are a population of equipment. So you need to multiply by that number of equipment. Mean downtime, normally how it is estimated, you just take data on the single downtimes, and maybe you want to take the average, and that's average means the mean, so that's the mean downtime. So again, with similar to MTBF, it's better to use statistical distribution to estimate these. You don't want to just assume. If you calculate your mean time between failure to be 5 years, if you're going to anticipate any future failures and so on, you don't say after 5 years I'm going to have a failure. It's only it's most likely that you will have it after 5 years. This is the most likely, but it doesn't have to be 5 years. It can be 4 years, it can be 6 years, and so on. So there is a probability component into this, and the best way to calculate it is to fit a probability distribution into this. Now, what is the reliability of our system that we just discussed, the low lift pumps? Is it a system in parallel? Is it a system in series and so on? It's basically a single piece of equipment. So we need to talk about basically the reliability of systems. So there are a number of reliability of system. There is the reliable systems in series, for example. And what systems in series are is basically if you need all the equipment all together, these are called system in series reliability wise. And if you need one only out of many, then this is called a system in parallel. And basically the reliability of system in series, you multiply the reliabilities together. But when you have a system in parallel, what you do is you multiply actually the unreliability together. So the unreliability of this system is, the unreliability of this component is 0.1 because the reliability is 0.9. So what you're gonna do is you're gonna multiply 0.1 times 0.1 times 0.1, in this case, for example, and this is the unreliability. To get the reliability, you subtract it from 1 again. And there are, of course, combined system where you have components in series, and all of these are actually put together in parallel. And the calculation is very simple. You calculate these in series, you calculate these in series, and the result basically, you get them to calculate the system in parallel. And there is a K out of N where the system in series is basically you need them all. The system in parallel, you need only one of them, but K out of N, if you need 2 or 3 out of N, so these are called K out of N system. Our lift pumps, our low lift pumps basically, they're none of these. They're not system in series, they're not system in parallel, and neither they are system of K out of N system. So in this case, you probably need to use either softwares or you need Markov approach, and basically you set up your reliability equations as such. So basically for this equipment, we have 16 possible scenarios, 12 of which are success states and 4 are failed states. What do we mean here? What we mean here, if we have all the 3 small pumps up and running and all the 3 big pumps up and running, this is called a success state. This is an apparent success state. if you have all this last one here, if you have all the small pumps and all the big pumps failing, so this is a fail state. If you have only one big pump, this is a fail state because you can only deliver what, 60,000. And if you have two small pumps, you can only deliver 70,000 when the requirement is 80,000. So this is a fail state. And of course, if you have one small pump only, then this is a fail state. So we took the data and it was from the CMMS, basically data collected over 18 years. We calculated the MTBF and we calculated the mean downtime, and the MTBF was 5 years and the downtime was 1 year. So is this good or is it not good? What we need to do is actually put it into our model, and this is the model can be just as simple as this one, although it looks complicated, but this is nothing but an Excel sheet actually and matrix multiplication. And what we got here, the solution for the current system as is was 99.9%. And this was a bit of a surprise, but that's the question. Now 99.9% availability, we need to gauge it against something. Is this good? Is 99% good? This is a question. Many people, when we say 99% is good, is it good? They say, yeah, 99% is good. But when you think about it, what is 99%? 99% means that if you have a year of 365 days, 1% of that is 3.5 days. Imagine going and telling a facility manager that it's okay, your system is good, it's reliable, 99%, and it's only going to be out of service for 3.5 days a year, which is this is what a 1% is. I don't think they're gonna like this very much. So don't get so hang up with numbers like 99 and 99, but 99.9 is actually a good number. And how do we do it? We actually compare it. Oh, why am I getting this message here? Okay, so now let's say we want to improve a system like this, and we say, what is more effective? Is it more effective to improve the MTBF, or is it more effective to improve the mean downtime? And this big system is actually very, very redundant, so the results are not going to show very clearly. But if we choose a simpler system here, where there are two pumps running in parallel, and you only need one, so with an MTBF of 5 years and a downtime of 1 year, let's see if we improve the MTBF, what will happen, or if we improve the mean downtime, what will happen? Why am I not being able? Can you hear me?
Yeah, we hear you.
Okay. So if you have, let's first fix the mean downtime. Let's say we have a mean downtime is 12 years. And the mean time between failure is 5 years. Let's say we want to improve the mean time between failure. Let's say we go what? How much improvement can we make? Pumps normally in 5 years is a good number. Let's say we're able to put them to 7 years. The improvement is going to go from 82% to 87%. What if we go to 10 years? That's 90%. Which it's very difficult to actually go to 10 years as a mean time between failure. But if you fix the MTBF to 5 years and you try to improve the mean downtime, and look at this. It's easy to improve your mean downtime from 12 months to 6 months, and look, you get an improvement from 82 to 90%. And if you improve it to 3 months, you get 95. And if you improve it to one and a half month, which is which is achievable, then you could actually, so maybe your time is better and effort is more better invested in improving the downtime than in improving the mean time between failure. Just to complete this story, what happened to it? So basically, some people decided, no, we want to look into replacing these pumps. Let's look at the if it is cost effective or it's not cost effective. So we went to the facility planning department. We told them, what if we're going to replace these pumps? They said, okay, if you're going to replace them, then we're going to give you 3 50%ers. That means if your requirement is 80,000, we're going to give you 3 pumps, 40,000, 40,000, 40,000. So we calculated the availability for this alternative solution, and we basically got a similar availability, assuming that the mean downtime is just a month and a half for this equipment. So in the basis of availability, it's only going to cost you money. You're going to spend basically $1 million in this project, and you're not going to get any improvement in the availability because your current system is actually capable of giving you the same availability. Well, they still came back and they argued, well, there is an extra capacity if you're diverting 15,000 GPM to the sea. This is expensive. Plus, if you're with your new alternative, you're only going to be maintaining 3 pumps where you're currently maintaining 6 pumps. So we did all of these calculations. We calculated the maintenance cost, the energy cost, and so on. And I don't want to go into these details, but we got basically a total of around $45,000 per year saving if we go to the alternative. But we will be spending $1 million. So if you go to, is this an attractive rate of return? Basically, it's not, because if you go to the company system, you will see that at least for a project to be attractive, you need to get at least around 11%, based on a 9% minimum attractive rate of return and a 20 years project life window, and that's basically the interest table equation for it. So it's not attractive to even financially, it's not attractive. You're not going to get in any more improvement. So this is the need for basically modeling reliability and availability. So I would like to end very quickly, maybe in 5 minutes, with some concluding remarks.
Yeah, Dr. Salman, we have remaining 5 minutes for the question.
I'll try to wrap up in 5 minutes. Okay. So reliability and availability improvement is a function of MTBF and is not mean downtime and mean downtime only, not just MTBF. And mean downtime might be more effective, cost effective to tackle. These are some concluding remarks. And basically, you cannot improve anything without being able to measure it. Let the numbers speak. Sometimes we come and we try to put our subjective judgment into the things. And also, mean time between failure is not mean time between work orders. Many people, when they calculate mean time between failure, they just see how many work orders and they calculate. So this is the wrong data analysis. Is very good. And it's always remember that it's all about risk mitigation. So how risk is exceeding downtime obligation is calculated. Let's take the following example, and I'd like to wrap up with it. Let's say you're obligated to finish to repair a pump or something in 3 weeks. And this is team 1, this is their performance, and this is team 2, this is their performance. This team 1, they on average, they finish in 2 weeks. This group, they finish in average, they take longer to repair the equipment. And let's add to it that these people have a history of not exceeding the obligation of 3 weeks. So which one is a better performer? Many people will know that this is a better performer than this one, but they can't really explain it with numbers. So what it is? The way to calculate it, very quick, is this is how you calculate risk. And it's all about sigma and so on. The way to calculate this is you take your mean, and this is your obligation. You see the distance between this guy and this guy here. So the distance is 1 here. You divide it by the standard deviation, and you get a sigma level of 2. So this is a 2 sigma performance here. But if you look at this one here, the distance is actually 0.7 from here to here. You divide by the standard deviation, you get a much higher sigma level. So basically this guy is 2 sigma performance. This guy is a 23 sigma performance. Of course, this guy is much higher reliable than this one in meeting the customer requirement, but you need a number for it. You can't just say, well, it looks like this one is better than this one. Prove it to me with numbers, and this is how to improve it. Why do we care about the number of sigma? Basically, depending on this sigma level, you can see how much risk you have. So if you are a 2 sigma level, then your confidence is 98%. While if you are a 1 sigma level, you're only 80%. So this is very important. If you are a 6 sigma level, then your risk is only 3.4 in a million. So if we want to improve the downtime in this case, what do we need? Basically, we need to work in 3 things. Either we shift this 3 up because we want to increase distance. How do we shift this up? This is the obligation. This is how our customer is expecting from us. Perhaps all we need to do is go and talk to him. Say, hey, we cannot finish it basically in 3 weeks. We need an extra 1 week to give us. And sometimes it's just as easy as this. People, your customer would like to know, give them a word and stick to your word. Or you can shift your mean and it can be as easy as just starting early. And this is what we did actually in these pumps. We started earlier. We've included these pumps into the company total repair program, where they actually get all the spare parts ready. So you don't just come and dump it to the workshop and say, I need it tomorrow. But if you plan for it earlier, then you can start actually working in these much earlier in time. The third element is trying to reduce this variation. And how do you reduce the variation? Basically, you reduce the variation by standardization, basically. So how do you reduce the variation? Don't leave things to randomness and luck. Have your procedures drawing ready all the time. So it's not like when you need the job, I'm going to look for my drawings, for my procedures, for the skilled worker. And make sure that you have the right tools, the right trained people. And all of these as actually simple tools. You find them in any quality program. Six Sigma, for example, there's a lot of tools in this toolbox. Go and use some of these and you will be able to reduce your variation. So what will happen now? And this slide is my last slide. If you're able to move this up from 3 weeks to 3.5 weeks. So you're currently, let's say you're required to finish within 3 weeks. You go, you talk to your customers and you get them to agree that you give you just 1/2 a week extra, okay? And you're able, let's say, to reduce your mean from 2 weeks after start to 1.5. And you're able to compact your standard deviation or your scatterness from 0.5 to 0.3, which is all easy to do if you actually put your head to it. The sigma level here is 2 and it corresponds to 5%. So what is the sigma level here? The sigma level here is basically you subtract these two numbers, 3.5 minus 1.5, that's 2 weeks, divided by 0.3, you get 6 sigma. And what does 6 sigma means? That means now, if you are able to change just these few parameters, you will be able to shift from 5% risk, and 5% risk is very high, to basically 3 in a million chance that you will not be able to meet your customer requirement, basically. So with this, I guess I conclude my presentation.